So today I wanted to talk a little bit about how the names of muscles are derived, as studying anatomy can be quite challenging, from remembering the names of muscles to knowing their insertion, origin, innervation and function. And it's sometimes difficult just to remember the name of a muscle, let alone all the other structures that are associated with it. So in this tutorial, we're going to discuss how muscles get their names in order to help make it easier for you to identify muscles and to remember them. And there are quite a few basic conventions when it comes to the naming of a muscle. And once you understand these basic conventions, it becomes much easier to identify them. So in the following slides, we're going to have a look at some basic methods used to name or derive the name of a muscle, which usually take into account one or more characteristics of the muscle. And these characteristics include shape, size, orientation of fibers, action, number of origins, origin and insertion, function, and location. And we'll talk a little bit about each of these as we go along. So let's have a look at the first way we can derive a name for a muscle, and that's from the muscle's shape. And if we look at our image over here on the right, of course we have an image of the deltoid in green here, shaped like a triangle. And since the muscle has a fairly well-defined shape, we can assume the triangle might have some significance in the naming, and sure enough, the Greek letter delta, when written, is shaped like a triangle and therefore gives rise to the name deltoid. And so the name for the deltoid muscle arises from its shape. Let's also have a quick look at the trapezius muscle, which we can see has a diamond shape. And of course you can see that the name of the trapezius is derived from the word trapezoid, which refers to the muscle's four-sided shape. The quality of a muscle with its regard to its dimension can also be used to derive the name of a muscle. And in this case, we're looking at a muscle whose main attribute is its flatness. The French word plat means flat, and so from that we get the word platysma for the platysma muscle that covers the superficial aspect of the muscles of the neck. In the case of the serratus anterior muscle, as you can see, the anterior attachments of the muscle are shaped like the fingers of a saw, or like the Latin word serrare, which conveniently means saw, hence giving the name serratus anterior. In many cases, muscles also derive their names from the size of a muscle, and some of these terms that we use to denote the size of a muscle include vastus, which comes from the Latin meaning great, for example the vastus lateralis muscle, and as you can see on the image on the right, the vastus lateralis muscle is a large muscle that travels all the way down the length of the femur, hence the name great. The term major is also used to describe how large a muscle is, usually in comparison to another muscle, for example the pectoralis major muscle. And in contrast, the term minor, as you may have guessed, is used to describe a muscle that is the smaller of two similar muscles, as is the case with the pectoralis minor muscle. And the term maximus comes from the Latin meaning largest or greatest. And as we can see on the right here, the gluteus maximus muscle is the largest muscle in the pelvic region, hence the use of the word maximus. The term minimus is the Latin for least or smallest, and is also used in naming muscles such as the gluteus minimus muscle, which is the smallest of the three gluteal muscles, or in the case of the hand, the flexor digiti minimi muscle, which flexes the little finger. The length of a muscle can also be taken into account. For example, the word longus is used for long muscles, such as the longus capitis muscle, a long muscle of the head and neck. The word brevis, which is the Latin word for short, is used to describe short muscles, such as the abductor pollicis brevis muscle, which is a short muscle of the thumb. The muscles can also derive their names from the orientation of their muscle fibers. The terms used to describe the orientation of muscle fibers include transverse, oblique, and rectus. The term transverse, which is used in the naming of the transverse muscle of the tongue, is used to describe muscle fibers that run perpendicular to the midline. The term oblique is used to describe muscle fibers that run diagonally at an angle or slanting. A good example of this would be the oblique muscles of the abdomen. And here we can see the external oblique muscle, whose fibers, as you can see, run obliquely. And finally, the term rectus describes muscle fibers that run parallel to the midline, such as in the case of the rectus abdominis muscle, which is seen here. And the word rectus in Latin means straight, and can also be used to describe a muscle that runs straight. For example, the superior rectus muscle, which is one of the four rectus muscles that control the movement of the eye. The fourth quality that is taken into consideration when naming muscles is the action that the muscle facilitates. As such, muscles can be described as flexors, extensors, supinators, pronators, levators, depressors, rotators, adductors, abductors, sphincters, and tensor muscles. These actions are usually the inverse of each other, and we'll point these out as we go along. But it'll definitely help to think about these actions mostly in terms of pairs, as one counterbalancing the other. The so-called flexor muscles carry out flexion, which is the action of decreasing the angle between 2 points. And a good example of these muscles are the flexor muscles of the forearm. For example, the flexor carpi radialis, which is one of the superficial flexors of the forearm and is responsible for flexing the hand at the wrist joint or radial abduction. Next, extension describes the opposite action of flexion, and the extensor muscles are muscles that return the limb to its original position or straighten the limb. For example, the extensor indicis muscle straightens the index finger. Supination describes the action of turning the limb so that the palm of the hand or the sole of the foot faces upward or outward. For example, when the supinator muscle of the forearm contracts, it rotates the forearm and hand so that the palm faces upwards. Pronation, on the other hand, describes the rotation of the limb so that the palm of the hand or the sole of the foot face downward and inward. For example, the aptly named pronator teres muscles carries out this very action. The term levator is used to describe muscles that perform a lifting action. For example, the levator anguli oris muscle lifts or elevates the angle of the mouth when we smile. The term depressor is used to describe a muscle that carries out the opposite action of levator muscles, which is depression or pulling downward. For example, when we make a sad face, the depressor anguli oris muscle is responsible for pulling the angles of the mouth downward. Rotators, as the name suggests, are muscles that facilitate the rotation of a limb or circular motion about a joint. For example, the muscles of the rotator cuff, which although individually do not have the word rotator in their names, are called the rotator cuff muscles simply because this is the action that they collectively carry out. An example of one of these muscles of the rotator cuff is the supraspinatus muscle, highlighted here in green, and the supraspinatus facilitates internal and external rotation of the humerus. Abductor muscles facilitate abduction, which is the movement of the limb or appendage away from the midline. The abductor pollicis brevis muscle, for example, abducts the thumb or facilitates the movement of the thumb away from the midline. Adductor muscles, on the other hand, facilitate movement towards the midline, as is the case with the adductor pollicis muscles, which adduct the thumb, as you can see in this image. The term sphincter is used for muscles that close an opening, for example, the pyloric sphincter muscle. Finally, tensors describe muscles that tighten or make something rigid, like the tensor fascia lata muscle, which sustains tension of the iliotibial tract. So now we're going to have a little bit of a look at some muscles which derive their names from the number of points of attachment at their site of origin. And a good example of these muscles are the biceps brachii muscle, which has 2 points of origin, the triceps brachii muscle, which has 3 points of origin, and the quadriceps femoris muscle, which has 4 points of origin. And I'm sure you can see a pattern forming here. The term bicep comes from the Latin meaning two-headed, the bi meaning two, and the sep coming from the word caput, which means head. Following the same logic, the three-headed muscle is aptly given the prefix tri, and the four-headed muscle quadri. In addition to being able to be named after the number of points of origin of a muscle, muscles can also be named according to their point of origin and insertion. And one such example is the sternohyoid muscle, which is a muscle of the neck region that has its origins on the dorsal surface of the manubrium of the sternum and the sternoclavicular joint, and inserts on the body of the hyoid bone. And of course, there are also some muscles that have been named according to their function. For example, the Latin word rhisus means laugh, and therefore the muscle of facial expression that is used when a person is laughing is called the risorius muscle, and this muscle is sometimes simply referred to as the laughing muscle. Finally, some muscles are named according to their location in the body. For example, the tibialis anterior muscle is located in front of the tibia. Some muscles also derive their names after their position or location in reference to a similar muscle, and in that case, the following terms would be used. Infra-inferior, meaning below or more caudally situated. Supra or superior, meaning above or more cranially situated, medialis, medial, middle, or medius, meaning in the middle or closer to the midline, intermedius, meaning intermediate, and lateralis or lateral, meaning to the side or away from the midline. An example of a muscle named using one of these basic terminologies would be a muscle we've looked at briefly before, the supraspinatus muscle, which is the more superiorly situated of the two spinatus muscles of the scapula.
Each time you take a step, 200 muscles work in unison to lift your foot, propel it forward, and set it down. It's just one of the many thousands of tasks performed by the muscular system. This network of over 650 muscles covers the body and is the reason we can blink, smile, run, jump, and stand upright. It's even responsible for the heart's dependable thump. First, what exactly is the muscular system? It's made up of three main muscle types: skeletal muscle, which attaches via tendons to our bones; cardiac muscle, which is only found in the heart; and smooth muscle, which lines the blood vessels and certain organs like the intestine and uterus. All three types are made up of muscle cells, also known as fibers, bundled tightly together. These bundles receive signals from the nervous system that contract the fibers, which in turn generates force and motion. This produces almost all the movements we make. Some of the only parts of the body whose motions aren't governed by the muscular system are sperm cells, the hair-like cilia in our airways, and certain white blood cells. Muscle contraction can be split into three main types. The first two, shortening muscle fibers and lengthening them, generate opposing forces. So the biceps will shorten while the triceps will lengthen or relax, pulling up the arm and making it bend at the elbow. This allows us to, say, pick up a book, or if the muscle relationship is reversed, put it down. This complementary partnership exists throughout the muscular system. The third type of contraction creates a stabilizing force. In these cases, the muscle fibers don't change in length, but instead keep the muscles rigid. This allows us to grip a mug of coffee or lean against a wall. It also maintains our posture by holding us upright. Skeletal muscles form the bulk of the muscular system, make up about 30 to 40% of the body's weight, and generate most of its motion. Some muscles are familiar to us, like the pectorals and the biceps. Others may be less so, like the buccinator, a muscle that attaches your cheek to your teeth, or the body's tiniest skeletal muscle, a 1 millimeter long tissue fragment called the stapedius that's nestled deep inside the ear. Wherever they occur, skeletal muscles are connected to the somatic nervous system, which gives us almost complete control over their movements. This muscle group also contains two types of muscle fibers to refine our motions even further: slow twitch and fast twitch. Fast twitch fibers react instantly when triggered, but quickly use up their energy and tire out. Slow twitch fibers, on the other hand, are endurance cells. They react and use energy slowly so they can work for longer periods. A sprinter will accumulate more fast twitch muscles in her legs through continuous practice, enabling her to quickly, if briefly, pick up the pace. Whereas back muscles contain more slow twitch muscles to maintain your posture all day. Unlike the skeletal muscles, the body's cardiac and smooth muscles are managed by the autonomic nervous system, beyond our direct control. That makes your heart thump roughly 3 billion times over the course of your life, which supplies the body with blood and oxygen. Autonomic control also contracts and relaxes smooth muscle in a rhythmic cycle. That pumps blood through the smooth internal walls of blood vessels, enables the intestine to constrict and push food through the digestive system, and allows the uterus to contract when a person is giving birth. As muscles work, they also use energy and produce an important byproduct: heat. In fact, muscle provides about 85% of your warmth, which the heart and blood vessels then spread evenly across the body via the blood. Without that, we couldn't maintain the temperature necessary for our survival. The muscular system may be largely invisible to us, but it leaves its mark on almost everything we do, whether it's the blink of an eye or a race to the finish line.
The primary purpose for the muscular system is to provide movement for the body. Now, these muscles receive their ability to move through the nervous system. There are 5 major properties to the muscular system. Number 1, muscles are excitable or irritable. This means that they are capable of receiving stimulation and responding to stimulation from the nerves. 2, they are contractible. After receiving stimulation, they are capable of contracting or shortening. Being extensible means a muscle can be stretched without damage by the application of force. With elasticity, a muscle is able to return to its original resting shape and length after being extended or contracted. The muscular system is adaptable in that it can be changed in response to how it is used. For example, a muscle will enlarge or undergo hypertrophy with increased work. But on the other hand, it can go into atrophy or waste away if deprived of work. Now, let's look at the 5 types of muscle movements. Number 1, adduction. Adduction is the moving of a body part toward the midline of the body. Abduction is moving a body part away from the body. Flexion means bending a joint to decrease the angle between 2 bones or 2 body parts. Extension is straightening and extending of the joint to increase the angle between 2 bones or body parts. And lastly, rotation involves moving a body part around an axis. The muscular system is divided into 3 main types of muscles, and each of these types can be moved by one of 2 ways, either voluntary or involuntary. The cardiac muscle is an involuntary muscle, meaning it operates without any conscious control. These muscles form the walls of the heart and contracts to circulate the blood. The visceral or smooth muscles are also considered involuntary. These muscles are found in organs or organ systems such as the digestive or respiratory system. And the 3rd type of muscle is the skeletal muscle. These are what we typically think of when talking about muscles. These muscles attach to the skeleton and provide the skeleton with the ability to move. The skeletal muscles are classified as voluntary. This is because we have to make a conscious effort or decision to make them move. Although muscles obviously make up the muscle system, there are still some supportive structures that we need to look at that are also a necessary part of the system. Tendons and fascia are important supportive structures for the skeletal muscles. Simply put, tendons are what attach a muscle to a bone, and fascia connects muscles to other muscles. Tendons and fascia work together with muscles, which create the muscular system necessary for movement. While not technically part of the same system, the nervous system is intrinsically connected to the muscular system of the body. It is essential to the voluntary skeletal muscles. If the communication from the nervous system is severed from the skeletal muscles will not be able to produce movement for the body. The body is now in a state of paralysis. This is known as quadriplegia. The only organ that is not directly dependent upon the nervous system is the cardiac or heart muscle.
Your muscle cells. They've got their own famous coupling, a pretty pair of tiny protein strands called actin and myosin. Deep down in the cells of your muscles, the hot protein action between actin and myosin is actually literally causing all of your motions. All of them. And I don't just mean voluntary stuff like walking down the street or moving your mouth so you can talk or chew chips, because your muscles also support your weight and help fend off gravity. The amazing thing about your complicated, self-healing, blood-guzzling muscle tissues is that they turn chemical potential energy into mechanical energy, or movement, simply by doing two things: contracting and relaxing. And that contracting and relaxing is exactly what's fueled by the constant coupling and separation of biology's greatest lovers. You're kept alive and moving by three types of muscle tissue: smooth, cardiac, and skeletal. Your smooth muscle tissue is found in the walls of all your hollow visceral organs like your stomach and airways and blood vessels, where it involuntarily and very usefully pushes fluid and other material around by contracting and relaxing over and over. Your heart is so important that it gets its very own muscle tissue type, cardiac muscle, which looks striped or striated and also functions involuntarily to keep your blood pumping without you having to think about it. The ones you can see and feel and flex are your 640 skeletal muscles. They're striated like cardiac muscle tissue, but they're also mostly voluntary, meaning you have to think about using them and activate them with your somatic nervous system. Most of them attach to your skeleton and create movement by pulling bones in different directions as they contract. Each one of your different skeletal muscles, like your biceps brachii or vastus lateralis or gluteus maximus, is technically its own organ made up mostly of muscle tissue, but also of connective tissue, blood vessels, and nerve fibers. And because your muscles are voracious energy hogs, each one is rigged up with its own personal nerve to stimulate contraction, and its own artery and vein to keep it well fed with all the blood and oxygen and nutrients it needs to operate. But to understand those operations, we first need to get a grip on the anatomy of a skeletal muscle, which involves fibers within fibers and lots of layers. Basically, a skeletal muscle is constructed like a really sturdy piece of rope. Thousands of tiny parallel threads called myofibrils squished together to form muscle fibers, which are your actual muscle cells, cells with mitochondria, multiple nuclei, and a cellular membrane called a sarcolemma. Those muscle fibers then form larger string-like bundles called fascicles, which combine to form the larger rope-like muscle organ like your biceps brachii. Overall, this bundles of bundles configuration makes muscle tissue fairly sturdy, but considering how much abuse your muscles take when you do something like pretty simple, like lift a big bag of dog food, it's no surprise they need a little help. That's why every muscle contains a few different kinds of supportive sheaths of connective tissue, the protective reinforcements to keep that bulging muscle from bursting. So that is the structure part of the story. But if you want to get into the nitty-gritty, the down and dirty of how you actually move, well, there are rules. Really just two main rules, and they have to do with proteins. And they're both true for a lot of the proteins we talk about, whether they're enzymes or ion channels or receptors or muscle proteins. And these rules are: 1. Proteins like to change shape when stuff binds to them, and 2. Changing shapes can allow proteins to bind or unbind with other stuff. So keep those rules in mind while we see how a muscle fiber contracts and relaxes. Now, remember those tiny myofibrils that bundle up to form your muscle fibers? They're divided lengthwise into segments called sarcomeres, which contain two even tinier strands of protein, two different kinds of myofilaments called actin and myosin. A sarcomere contains both thin filaments made up mostly of two light and twisty actin strands, and thick filaments composed of thicker, lumpy-looking myosin strands. Each sarcomere is separated by what's known as a Z-line at either end, which is just a border formed by alternating thin filaments in a kind of zigzag pattern. A muscle contracting is all about sarcomeres contracting, bringing those Z-lines closer together. When your muscle cells are at rest, your actin and myosin strands don't touch, but they really want to. Specifically, that club-headed myosin wants to get all up close and personal with the actin. When this happens, and it will eventually, it's called the sliding filament model of muscle contraction. But in the meantime, like in any good love story, the pair have some obstacles to overcome. Namely, actin is blocked by a couple of protein bodyguards called tropomyosin and troponin, which keep getting in the way. Luckily, these guards can be bought off with a little ATP and some calcium. Remember, ATP is kind of like molecular currency. It contains chemical energy, and your muscles are all about converting chemical energy to motion, so they're always hungry for more ATP. Your muscle cells have lots of nuclei, but some of them also have a lot of mitochondria, whose sole purpose in life is to crank out ATP. And muscle cells also have their own version of an endoplasmic reticulum, the cell's transport and storage system, but in this case it's specialized, so it gets a special name, the sarcoplasmic reticulum. Its walls are loaded with calcium pumps, which use use ATP to save up a bunch of calcium ions. And it's also studded with calcium channels that are linked to voltage-sensitive proteins in the membrane of the muscle cell. Say I want to move my arm. My brain sends an action potential along the motor neuron until it synapses with a muscle cell in my arm. The receptors on that muscle cell are ligand-gated sodium channels. So when the motor neuron releases our old friend acetylcholine into the synapse, the channels open up and create a rush of sodium into the cell as a graded potential, which, if it's strong enough, causes nearby voltage-gated sodium channels to open. Now I want to take a second and point out here that we're still talking about an action potential, but not in a neuron. This is happening in a muscle cell, people. So that action potential zips along a muscle cell's membrane, the sarcolemma, which has lots of tubes that run deep inside the cell called T-tubules. When the action potential travels down one of those tubes, it eventually triggers the voltage-sensitive proteins that are linked to those calcium channels in the cell's sarcoplasmic reticulum. When those channels are thrown open, the calcium stored inside rushes into the rest of the cell, and finally myosin is like, yes, here we go! At this point, the myosin is totally stoked, because the bodyguards that have been frustrating it are in for a big, irresistible distraction. That's because the protein troponin just loves to bind with calcium, and remember, when stuff binds to proteins, the proteins change shape. So the calcium latches onto the troponin and causes it to pull the other bodyguard protein, the tropomyosin, away from the sites on the actin strands that the myosin really wants to get its paws on. The only myosin heads that can bind to those newly exposed sites are the ones that are ready for action. That is, the ones that have already grabbed a molecule of ATP that's been floating around and broken it down into ADP and the leftover phosphate. When a myosin head does that, it moves into an extended position, kind of like a stretched spring, still holding on to the ADP and the phosphate, and still storing the energy that was released when they were broken apart. So after all that, with the myosin primed for action and the bodyguards out of the way, the myosin finally binds to actin, and it is beautiful. When they bind, the myosin releases all that stored energy, and in the excitement of it all, the myosin changes shape. It pulls on its precious actin strand, kind of like pulling a rope hand over fist. In the process, it shrinks the whole sarcomere and contracts the muscle. That's the sliding part of the sliding filament model. Now, with its energy spent, that little head has no use for the ADP and the phosphate, so they unbind with it because, remember rule number 2, changing shape encourages proteins to bind or unbind with stuff. That unbinding causes a small change in its shape, which lets a fresh ATP bind there in its place. That binding causes another shape change, but this time it causes the myosin to release from the actin. This is when the myosin breaks down its new molecule of ATP into ADP and a phosphate, which moves it into the armed position yet again, getting it ready for its next rendezvous. And meanwhile, those calcium pumps are working hard to restock the calcium in the sarcoplasmic reticulum, so they start grabbing the calcium that's floating around, causing calcium to unbind from the troponin. When it unbinds, the resulting shape change puts the tropomyosin bodyguards back into place. It keeps repeating itself many, many times every moment while I sit here and talk, and while you sit there and eat and text and take notes, the whole drama replaying itself over and over. Kinda like you'll have to play this video over and over again to get all the little steps of the sliding filament model straightened out. But hey, some stories get better the more you hear them. You've probably heard somebody refer to a really difficult, onerous task as the heavy lifting. Or maybe when someone else tells you that you have to do hard work on your own, they'll say, you can't have somebody else do your push-ups for you. So yeah, often when we're talking about hard work that we just don't want to do, we use metaphors that involve the skeletal muscles. And yeah, that's their reputation. They're what you use to perform all of the necessary but sometimes unpleasant brute force exertions that life requires of us. But they do a lot more than just heavy lifting. Your skeletal muscles, 640 in all, come in all different shapes and sizes, from the longest, the sartorius in your upper thigh, to the biggest, the gluteus maximus in your butt, to the tiniest, the stapedius in your middle ear. The same muscles you might use to pluck an eyebrow, or catch a firefly, or cuddle a kitten, can in other circumstances crush cans, or punch holes in walls, or do a bunch of push-ups. Which, by the way, are not really a thing. And she's gonna prove it. That's right, I'm gonna have somebody do my push-ups for me. Now, when you look at how the muscular system moves, you gotta keep two things in mind. First, muscles never push, they always pull. Now, how can that be, since Claire here is obviously pushing herself up? Well, remember that most skeletal muscles extend over joints to connect to at least two different bones. That's why they're skeletal. When a muscle contracts, the bone that moves is called the muscle's insertion point, and the muscle brings the insertion closer to the bone that doesn't move, or at least moves less, and that's called the muscle's origin. And that movement is always a pull, with the insertion bone being drawn toward the origin bone. And when you think about it, it has to be this way. Muscles can't, like, extend themselves beyond their resting state to push a bone away from it, so even though Claire's pushing herself up off the ground in an exercise we call push-ups, her muscles are actually pulling their insertions toward their origins. When she pushes herself up, her pectoralis major is contracting, pulling its insertion point, which in this case is the top of her humerus, toward the immobile origin, which is her sternum. Every single movement that your skeleton makes uses the very same principle, whether you're hammering on an anvil or lifting your pinky to sip a cup of tea. So that's the first thing. The second big thing to remember about skeletal muscles is that whatever one muscle does, another muscle can undo. You can generally classify skeletal muscles into 4 functional groups depending on the movement being performed. For example, the muscles that are mainly responsible for producing a certain movement are called that motion's prime movers, or agonist muscles. So when Claire does jumping jacks, she's using those pectorals in her chest and latissimus dorsi on her back to adduct her arms back down to her sides. Put another way, those are her prime mover muscles for adduction. At the same time, there are antagonist muscles that are working in reverse of that particular movement by staying relaxed or stretching or contracting just enough to keep those prime movers from overextending. So in this case, the antagonists of the jumping jacks would include the deltoids on top of her shoulders, which among other things help her slow down her arms so that she doesn't slap her thighs too hard. But when it's time to start abducting her arms from her side to over her head, those deltoids now become the primary movers, while the pecs and lats switch to being antagonists. The third functional muscle group is your synergists, and they help the prime movers usually either by lending them a little extra oomph or by stabilizing joints against dislocation. With all these arm movements, most of the rotator cuff muscles, like the teres minor or the infraspinatus, are acting like synergists. So this is how skeletal muscles are functionally grouped, but what about their actual functions? As individual organs, how do they contract to create both quick and sustained movements and to regulate force? How can Claire's hands gently pet this corgi in one moment and then crush a can in another? I got 2 words for you. Motor units. A motor unit is a group of muscle fibers that all get their signals from the same single motor neuron. Since all those fibers listen to only one neuron, they act together as a unit. In a big power-generating muscle like your rectus femoris in your quad, each of 1,000 or so motor neurons may synapse with and innervate 1,000 muscle fibers. Those 1,000 fibers together form a large motor unit, and big units are typically found in muscles that perform big, not very delicate movements, like walking and squatting and drop kicking. But other muscles, like the ones that control your eyes and fingers, which exert fine motor control, may have just a handful of muscle fibers connected to a single motor neuron. Those relationships are small motor units. And when a motor unit, no matter how large or small, responds to a single action potential, those fibers quickly contract and release in what we call a twitch. And every tiny twitch has 3 distinct phases. To understand which happens when, we gotta go back to the sliding filament model. Immediately after a muscle fiber is stimulated by a nerve, when calcium ions are flooding into the sarcomeres to pull away those 2 protein bodyguards of tropomyosin and troponin from the actin, that's called the latent period. The stimulus has arrived, but no force is being produced. That's when the action is just starting. Then comes a brief period of contraction when the myosin heads are binding and pulling and releasing over and over, and the muscle fibers contract. But soon the fiber slides back down into the relaxation period when the calcium gets pumped back into the sarcoplasmic reticulum, and the actin and myosin stop the binding cycle, and the muscle relaxes. Each phase consists of a lot of little steps, and while you couldn't tell by watching my brother dance, the fact is that our muscular movements are pretty smooth. That's because one muscle can produce a variation of smooth forces called graded muscle responses, and they're generally affected by both the frequency and strength with which they're stimulated. So say Claire's trying to lift something heavy, like a paint can. Just as the volume of a sound corresponds to the frequency of action potentials from your ear to your brain, her brain gets her muscles to increase their force by increasing the frequency with which her motor neurons are firing. It's like pushing a button over and over again really fast. Lift! You can do it! Feel the burn! Or whatever. And the faster these nerve impulses fire, the stronger each successive twitch gets, since the muscle doesn't get a chance to relax in between. Because remember, the relaxation period of a twitch is when the calcium is being pumped back into the sarcoplasmic reticulum. If another action potential travels down before that can happen, even more calcium gets released, which ends up exposing more actin for myosin to bind to, and that means more force in that fiber. In this way, twitches end up adding to each other, as they get closer together in time, and that's what we call temporal summation. At some point, though, almost all of the actin binding sites are exposed, so all of the myosin heads can work through their cycles of ATP and ADP, and the muscle force can't increase anymore, even with faster action potentials and more calcium. When all those little twitches blend together until they feel like one gigantic contraction, that's called tetanus. At that point, any person on the planet will hit a ceiling of maximum tension. That tension means myosin and the calcium pumps are burning up the muscle cell's ATP, and the finite supply of ATP is what makes it impossible to maintain vigorous muscle activity indefinitely. Prolonged contraction leads to muscle fatigue, and when your muscles just can't take it anymore, all that tension crashes to zero. And remember, all of this twitching happens in individual motor units. Since twitches are driven by action potentials, and action potentials only have one intensity, frequency is the only way to create a grade of force. So when we zoom out to the complete muscle of maybe 1,000 motor units, we can increase the strength of the stimulus by sending action potentials to more motor units. If amping up frequency is like hitting a button again and again, then increasing the signal strength is like smashing the whole keyboard. Multiple action potentials don't travel down all the motor neurons at exactly the same time. Each motor unit twitches at slightly different times, which helps smooth out the twitchiness. So contractions intensify as your motor neurons stimulate more and more muscle fibers. This is a process called recruitment, or multiple motor unit summation, and it's where some of your muscle's more nuanced abilities come in. So let's say Claire is holding Abby. She wants to hold on to her tight so that Abby doesn't fall, but not too tight, right? So to increase the contraction force and tighten her grip, she can recruit another motor unit. Recruiting one with 20 fibers will firm her grasp, but calling on one with 1,000 fibers might... well, let's not think about that too much. Lucky for our corgi friend, this recruitment doesn't escalate at random, it follows what's known as a size principle. It starts when the smallest motor units with the smallest fibers are activated by your most excitable neurons, then some larger motor units with larger fibers are enlisted, increasing the strength of contraction. And finally, if you want to give it all you got, which you don't in Abby's case, your largest motor units with your biggest muscle fibers will get involved. These big guns are the last to join up, in part because they're controlled by your largest and least excitable motor neurons. But when they're in, they are all in, packing 50 times the force of those smaller fibers. So the basic rule is the more motor units recruited, the greater the force that's generated. Now that we know how muscle contractions happen, let's look at our two main flavors, isotonic and isometric. Say I want to pick up my crash course mug. Well, I can do this workout myself. If the temporal and recruitment summation triggers enough muscle tension in my arm to overcome the weight of the load and lift the mug, changing the length of the muscles involved during contraction, then that is an isotonic movement. Now if I tried to pick up a building, I could contract my muscles all I wanted and develop a lot of tension without actually changing the muscle's length, in which case I'd be experiencing isometric contractions, and possibly a hernia.
The current theory of how a muscle cell contracts is the sliding filament theory, which states that the contraction of a muscle cell occurs as the thin filaments slide past the thick filaments. During contraction, the sarcomere shortens and the thin and thick filaments overlap to a greater degree. The sliding filament theory of how a skeletal muscle contracts involves the activities of 5 different molecules plus calcium ions. The 5 molecules include myosin, actin, tropomyosin, troponin, and ATP. In addition to these 5 molecules, calcium ions are also involved in the process of muscle contraction. In skeletal muscle cells, the myosin molecules are bundled together to form the thick filaments. The shape of an individual myosin molecule is similar to a golf club with 2 heads. Myosin has several important functional features. The head, or cross bridge, has the ability to move back and forth. The flexing movement of the myosin head provides the power stroke for muscle contraction. Another feature of the myosin molecule is the hinge portion of the linear tail. This allows vertical movement so that the cross bridge can bind to actin, the thin filament. The cross bridge has two important binding sites. One site specifically binds ATP, adenosine triphosphate, a high-energy molecule. Notice the position of the cross bridge. This is called the low-energy conformation. The binding of ATP transfers energy to the myosin cross bridge as ATP is hydrolyzed into ADP and inorganic phosphate. Now the cross bridge is in its high-energy conformation. The second binding site on the myosin cross bridge has a strong attraction for binding to actin. Thin filaments are composed of three molecules: actin, tropomyosin, and troponin. Actin is the major component of the thin filament. The actin portion of the thin filament is composed of actin subunits twisted into a double helical chain. Each actin subunit has a specific binding site to which the myosin cross bridge binds. The regulatory protein tropomyosin is also part of the thin filament. Tropomyosin entwines around the actin. In the unstimulated muscle, the position of the tropomyosin covers the binding sites on the actin subunits and prevents myosin cross-bridge binding. To expose the binding sites for binding with myosin, the tropomyosin molecule must be moved aside. This is facilitated by the presence of a third molecular complex called troponin. Troponin is attached and spaced periodically along the tropomyosin strand. Troponin by itself is not able to move the tropomyosin away from the binding sites. This process requires calcium ions. After an action potential, calcium ions are released from the terminal cisternae and bind to troponin. This causes a conformational change in the tropomyosin-troponin complex, dragging the tropomyosin strands off the binding sites. The 5 organic molecules and the calcium ions function together in a coordinated manner to cause the thin filament to slide past the thick filament. We will first show an animation of a single cross-bridge cycle and then describe this process step by step on the following pages. As you've just seen, cross-bridge cycling is a continuous event. For the purposes of easier understanding, however, let's break it down into 6 separate steps. 1. The influx of calcium triggering the exposure of binding sites on actin. 2. The binding of myosin to actin. 3. The power stroke of the cross-bridge that causes the sliding of the thin filaments. 4. The binding of ATP to the cross-bridge, which results in the cross-bridge disconnecting from actin. 5. The hydrolysis of ATP, which leads to the re-energizing and repositioning of the cross-bridge. And 6. The transport of calcium ions back into the sarcoplasmic reticulum. The first step is exposing actin's binding sites. When a muscle cell is stimulated, the action potential brings about the release of calcium ions from the terminal cisternae of the sarcoplasmic reticulum. The calcium ions flood into the cytosol and bind to the troponin, causing a change in conformation of the troponin-tropomyosin complex. This conformational change exposes the binding sites on actin. When a binding site on actin is exposed, an energized cross-bridge can bind to it. The binding of myosin to actin brings about a change in the conformation of the cross-bridge, resulting in the release of ADP and inorganic phosphate. At the same time, the cross-bridge flexes, pulling the thin filament inward toward the center of the sarcomere. This movement is called the power stroke. The chemical energy of ATP has been transformed into the mechanical energy of a muscle cell contraction. In order to disconnect the cross-bridge from actin, an ATP molecule must bind to its site on the myosin cross-bridge. The release of the myosin cross-bridge from actin triggers the hydrolysis of the ATP molecule into ADP and inorganic phosphate. Energy is transferred from ATP to the myosin cross-bridge, which returns to its high-energy conformation. In the final step, calcium is actively transported from the cytosol back into the sarcoplasmic reticulum by ion pumps. As the calcium is removed, the troponin-tropomyosin complex again covers the binding sites on actin. The active transport of calcium involves specialized ion pumps in the membrane of the sarcoplasmic reticulum. These pumps must be energized by ATP. In contracting muscle, we see multiple cross-bridge cycles. Here are 4 cross-bridges which cycle in a coordinated manner. Note that during a contraction, all cross-bridges are neither bound nor disconnected at the same time. In this view, several myosin and actin filaments are interacting to demonstrate the sliding filament theory of muscle contraction. Notice that although the sarcomere shortens, the length of each myofilament does not change. However, watch as the width of the H zone changes. Skeletal muscle cells contract as a result of impulses from motor neurons. The place where a motor neuron stimulates a muscle cell is called a neuromuscular junction. Skeletal muscle cells are electrically insulated from each other by endomysium. In order for skeletal muscle cells to contract, each cell must be stimulated by a process of a motor neuron. Each motor neuron is a single nerve cell extending from the brain or spinal cord to the muscle, where it can stimulate several muscle cells. The axon is the elongated process of the nerve cell that carries impulses to the muscle. The neuromuscular junction is the place where the terminal portion of a motor neuron axon meets the muscle cell membrane. Now let's take a closer look at a neuromuscular junction. The swollen distal end of the motor neuron axon is called the axon terminal. Within the axon terminal are synaptic vesicles containing the neurotransmitter acetylcholine. Notice that at the neuromuscular junction, the motor neuron and the sarcolemma of the muscle cell do not actually touch. The synaptic cleft is the space between the axon terminal and a folded region of the sarcolemma called the motor end plate, highlighted here in red. Recall that the sarcolemma is the general name for the muscle cell membrane. The T-tubules are invaginations of the sarcolemma penetrating deep into the interior of the cell. The terminal cisternae are specialized regions of the sarcoplasmic reticulum that serve as reservoirs of calcium ions, shown here as red dots. The sarcomere is the contractile unit of the muscle cell that extends from one Z-line to the next. The plus and minus signs on the axon terminal, sarcolemma, and T-tubules indicate a polarized condition called the resting membrane potential. Although plus and minus signs are not shown on the motor end plate, it is also polarized. Here's an overview of the activity that occurs at the neuromuscular junction. An action potential arriving at the axon terminal triggers the release of the neurotransmitter acetylcholine, resulting in the depolarization of the motor end plate. This depolarization triggers an action potential that propagates along the sarcolemma and down the T-tubules, causing contraction of the sarcomeres. When the action potential arrives at the axon terminal, the voltage change of the membrane opens voltage-regulated calcium channels, allowing calcium ions to enter the axon terminal. The calcium ions cause several synaptic vesicles to fuse with the membrane of the axon terminal. The neurotransmitter acetylcholine contained within the vesicles is liberated by exocytosis into the synaptic cleft. Additionally, calcium ions are pumped out of the axon terminal. Acetylcholine binds to receptor sites of chemically regulated ion channels on the motor end plate. This causes the channels to open, permitting an influx of sodium ions and a small efflux of potassium ions. This ion exchange causes a local depolarization of the motor end plate, which will be indicated here as a glow. Now the motor end plate is depolarized. After a brief period of time, acetylcholine diffuses away from its receptor site, and the ion channel closes. Acetylcholine is then broken down by the enzyme acetylcholinesterase. The depolarization of the motor end plate initiates an action potential which propagates along the sarcolemma in all directions and down the T tubules. The action potential causes the release of calcium ions from the terminal cisternae into the cytosol. Calcium ions trigger a contraction of the muscle cell. The activity at the neuromuscular junction as a continuous process,